let's start. Yeah. First, I go through all the questions of quiz 1, then quiz 2. If questions relatively easy, then I go faster. If sometimes I need to do more explanation. Yeah. All right, the first question. Yeah. When we solve some computing problems, sometimes it's a good idea to work on a few cases with small data sizes first. Yeah. Do some experiments. When we do experiments, we like to choose small problem sizes. Yeah. Then we can extend our solutions. Yeah, general case. It's correct. So it's basically some effective strategy we used a few times in this class. Yeah, a few times in this class. Yeah. Here we do not say this strategy can help us solve all the problems. No, yeah, some of the problems. Yeah. For some of the problems, it works effectively. Yeah, but for other hard problems, we have to use different strategies. Yeah. All right, so that's the first question. Second question, is the execution time stable measure? No. Yeah, so the reason is simple. In our notes, we look at it from hardware point of view and a software point of view. Yeah. Hardware, the machine, how fast your computer is. Yeah, so it could be very different. Yeah. Software part, implementation, good implementation and a bad implementation, the difference could be big. Yeah. All right. So number 3, nanosecond. Yeah. It's a simple question. C. Yeah. 10 to the negative 9. Yeah. 1 billionth of a second. Yeah. Yeah. Simple question. Yeah. Number 4. Yeah. Number 4. Yeah. Actually, so here, for this question, basically you have 2 ways to find the answer. Yeah. All right, so two different methods. The first one, from the formula. From the formula, we know this formula, okay? Yeah. Yeah, right. And this one, we can factor 3 square out. So you need to see this property. Yeah. So in class, we factor 2 square out, right? So here, we factor 3 square out. Yeah. Then, what do you need to do? 3 square times 3 square times 1 over 6 n plus 1 to n plus 1. Simplify this 3 half, right? 3 half. So look at this one, right? Yeah. This one. So that's the first method. Second method, second way, testing. Yeah. Plug in a few relatively small n numbers. Let's say n equals 1, 2, 3, if necessary. Yeah. If it's enough to see the difference. So when n equals 1, so this one gives you 3 square. So n equals 1, you get a 3 square, and you look at which option gives you 3 square. Okay? Yeah. So for those who are not equal to 3 square, then you eliminate them. If you still have more than one, then you need to try 2. 2 should be 3 squared plus 6 squared. Okay? Yeah. And see if you can eliminate all the options except one left. So you want to have only one left. Otherwise, you need to do more experiments, testing. So this testing way, especially when you do not know the formula. So sometimes you may not know the formula, right? For example, I may give you a similar question like 1 cube plus 2 cube plus 3 cube, okay? Plus to n cube. You may not know the formula. Although you can search on web to find the formula. It's very easy to find the formula. But if you do not know the formula, then you can do testing. All right. So these two commonly used methods. All right. Number 5. Horner's rule. This question, I use it to check if you are familiar with our notes. In our notes, we went through the details of Horner's rule, and especially we talk about the factorization property a lot. Actually, we apply the factorization property as much as we can, right? As much as we can. And that's the greedy algorithm. So, so I talk about the greedy algorithm, the factorization. All right. Number 6, when we evaluate a general polynomial, do we have multiple ways? Yes, that's simple. In your project, you use multiple ways, right? In your project, you use at least 3 different methods to evaluate the same polynomial. So this question looks so simple, but so the reason I made this question, still make sure you are familiar with our materials. Because some of the students, they may not be familiar with our materials. Some students, they skip the videos, not quite familiar with our notes. Then they answer the questions based on their intuition. If they use their intuition, they only know one way to evaluate a polynomial, the brute force way. That's the way they know. Other than the brute force way, they do not know any other. Because it's not easy to see a different way to evaluate polynomial other than the brute force for those students who are not familiar with our notes. So that's the reason, I designed this simple question for those students who are familiar with our notes. All right. Number 7, since the linear search is too slow, that's true. Linear search, in most of the cases, very slow. If we use asymptotic notation, we use big theta of n. It is basically useless to solve any real-world problem, but the conclusion is wrong. It's still useful. We cannot say it is basically useless. Because sometimes, if our data, so we need to look at our data. If our data is unordered, we cannot apply the binary search. No, the binary search is one of the topics in our module 4. So after insertion sort, then I will talk about binary search soon. So But if the array, the data is unordered, you cannot use the binary search. And sometimes you have to use the linear search. We know it is slow, but in some situations, that's the only way you can do it. Okay, so it is still useful. Yeah. All right. That's the, Yeah. Number 8. When we apply a linear search on a given array, which of following? Unordered. Unordered. So remember, in class I mentioned 1 point. Because the data could be ordered sometimes. So our linear search, we expect the array is unordered, but sometimes the given data happens to be ordered, right? Happens to be ordered. So that could happen. So the data happens to be ordered. Okay? In that case, if it happens to be ordered, well, because we don't know, right? We do not know it is ordered. Our algorithm does not know it is ordered. Okay? So our linear search algorithm does not detect if it is ordered. Our linear algorithm implementation, in general, we do not do the detection. The reason is too expensive. Too expensive. We don't want to spend many comparisons to detect if it is ordered. Too expensive. So we just assume it's ordered. Even if it is ordered, we still treat as unordered to run the linear search. Okay? So try to understand that point. That point. Because the detection is too expensive. So we don't want to pay that much cost for the detection part. All right. Number 9. Is it possible that one can find a special polynomial? So this one. I need to explain a little more. So first, to answer this question, you need to be familiar. First, I'll give you the answer. Answer is yes. Is it possible that one can find a special polynomial with n terms? Special polynomial with n terms. Not one term. One term we know it's easy, right? One term we can use repeated squaring. It's easy. But here, I tell you the condition. It must be a polynomial with n terms, such that the value of this polynomial can be calculated with less than 0.01% times n of n multiplications. N terms, that multiplications. The answer is yes. So this question, you need to know several important knowledge points in our notes. The first is the Pascal's triangle. First, you need to know, the critical piece, Pascal's triangle. How to get a polynomial with n terms? We wanted you follow that Pascal's triangle. Okay, Pascal's triangle, right? So that polynomial, P yeah, P sub m, Pascal's triangle, can we get 1 plus 1 to the n? Yeah, because its expansion corresponds to Pascal's triangle, right? Yeah. All right. And this one, although we know it gives n plus 1 terms, right? N plus 1 terms. But n plus 1 terms and n terms, the difference is only 1. We just change that n number, okay? Yeah. So that's the same. So n plus 1 terms. All right. But to evaluate this polynomial, think about if n is the power of 2, 2 to the k. Think about if n equals power of 2, yeah, by repeated squaring, so you need to know the repeated squaring technique. We just need k multiplications, right? Okay? So we just need k multiplications. So n equals 2 to the k, we just need k multiplications. See? Now, let's answer the question. So let's look at the ratio k over 2 to the k. Yeah. We need the k multiplications, and the degree is 2 to the k. We know the limit is, when k goes to infinity, the limit is 0, right? The limit of this ratio is 0. Is 0 less than, is this 0 number less than that 0.01%? That means when k is sufficiently large, their ratio is less than 0.01%. Okay? So when k, so here, let me write the conclusion. So based on this limit tells us when k is sufficiently large, here I use this word, sufficiently large, okay? Yeah. So you know the meaning, sufficiently large. So we have, based on that limit, we have k is less than 0.01% times 2 to the k. And 2 to the k is n. Based on our assumption, 2 to the k is n. Okay? So this k. So to answer this question, you need to know this much. Okay? Yeah. From our notes. All covered. Yeah. So we discussed, we cover all the pieces here. So you can, put the pieces together, to make the puzzle. All the pieces in the puzzle. You have all of them. Yeah. Yeah. So this is the hardest question in this quiz. Yeah. Yeah. Other than this one, all other pretty simple, straightforward. But this one, you need to do thinking. You need to have the knowledge of all these pieces here. Yeah. And also the limit view. Yeah. Yeah. Limit view. Yeah. All right. Yeah. Although you can use intuition. Yeah. So for the limit part, you can use your intuition. Yeah. Yeah. Not necessarily use the limited language. Yeah. All right. Yeah. Next question. The last one of quiz 1. Yeah. Given an array with n elements, is it possible that one can design algorithm find minimum with n minus 2? Answer is no. Yeah. All right. N minus 2 comparisons. Yeah. The reason is very simple. The reason is in class we show our n minus 1 comparison solution is optimal. Optimal. So that means nobody can improve it. Nobody can reduce the number of comparisons of an optimal solution by 1, even by 1. Yeah. It's impossible. Okay? Yeah. Yeah. So that's from that question. Yeah. So from this quiz, you can see all these questions are based on our notes. Yeah. But some of the questions you may not get the answer in a straightforward way, like question 9. So you need to put many pieces together. Okay? So not that straightforward. Question number 10 is straightforward. Yeah. So you only need to know the result. Optimal solution for the problem, finding the minimum problem. Then you can answer easily. Yeah. Yeah, but for question 9, you need to do a little more work. Yeah. All right? Yeah. Then question from quiz 2. All right, question 1. When we talk about the data size concept in the computing problem, we always mean that it refers to the number of elements in an array. Yeah. So we talk about this in class. False. Yeah. Because there is another case. Yeah. So this is just one case, but there is another case, magnitude. Of the number. Okay? Magnitude. How large is n? Yeah. The example, we have a few examples. One is the prime factorization of n, right? Of n. In this case, you only have one element, but the magnitude is its size. How large is this number? That's the problem size. Another one, we just learned in Module 3, Fibonacci number, right? Fibonacci number, f sub n. Given n, you need to find this n. The magnitude of this n is the, Fibonacci number. Sorry, it's the problem size. Is the problem size. Okay? Yeah. Another one you can, GCD problem, right? Greatest common divisor, GCD problem. So you need to find the GCD of m and n. GCD m and the problem size, you can use the maximum of m and n. The larger one of the two numbers. You can use that as the problem size. Yeah. Yeah. All right. Yeah. So there are many examples. We use magnitude as the problem size. Yeah. Question number 2. To evaluate a polynomial, the higher the degree it has, the more multiplications we need. Yeah. So this question, I want to explain something here. The answer is false. Okay? The answer is false, but we use this statement frequently. Okay? So I want to explain that little difference. Yeah. So first, this statement we use the frequent. Okay. All right. So let me write. We use this statement in our problem solving. We use this statement as a principle. Okay. We use it as a principle. Yeah. And when we talk about principle, we mean this statement, most of the time it is true. Okay? So this statement, it is true most of the time, but not 100%. Okay? But not 100% true. Okay? You can treat as 90-something% it is true. Yeah. So that's the meaning when we talk about, we use it as a principle. In principle, it is true. So it is useful. So 90-something% we can use it. But there is a small percentage, very small percentage, it is not true. It is not true. So when it is not true, we cannot use it in our problem solving. Okay? So we have to find a different way to solve our problems. Yeah. So that's the meaning of the principle. So that part is important. But here, this statement, in this question, we do not say in principle, right? We do not say in principle. If we do not say in principle as a statement, if it's true, it must be 100% true. So here, to answer the question here, if a statement is true, it must be 100% true. Okay? Yeah. So here the reason we pick false, because it's not 100% true. So it's 90-something% true, but not 100%. So as a statement, we say it's false. Yeah. But in our problem solving, if we use it as a principle, we can use it at approximately 90-something% of the time. Yeah. That's the difference. Okay? So that's the difference. Yeah. So be careful about that difference. Yeah. Yeah. All right. Number 3. Yeah. Which of the following types of problem does the problem finding the minimum array belong to? Yeah. Selection problem. Yeah. Selection. Yeah. Selection problem, we finding. So find the kth smallest element. That's the definition of the element of an array. That's the definition of the selection problem. And here, minimum k equals 1. Okay? Yeah. All right. Number 4, L'Hopital's rule to calculate the limit of the ratio. So we can always, it's false. Not always. Okay? Yeah. We need to check the condition. Check the condition first. Before we apply the L'Hopital's rule, we need to check the condition. The ratio must be an indeterminate. Form. Indeterminate form. And in our place, our situation, we have infinity over infinity indeterminate form. Yeah. But in math, there are more. Yeah. Yeah. So one student asked me in class, So more forms in math, okay? Yeah. But in our class, we only use this one. We only use one form. In our class, we do not have other cases, only this case. Yeah. So you need to know this condition before you apply the L'Hopital's rule. Okay. Yeah. Number 5, an exponential function with base greater than 1 always grows faster than that of any polynomial. True. So a to the n grows faster than polynomial. Yeah, polynomial, p of x. Okay, yeah. With a greater than 1. Yeah. And we prove it in class using the, L'Hopital's rule. Yeah. L'Hopital's rule. Okay. Yeah. Yeah. All right. Yeah. Actually, in class we didn't consider the the general polynomial. Yeah. So we consider monomial. Highest term. Highest term. Yeah. Yeah, but the highest term, actually, it's the dominant term, right? So it's enough to show that the dominant term still is dominated by the exponential function. Yeah, so it's good enough. Yeah. Yeah. So this number 6. Now, this one, if you are familiar with all the knowledge pieces we need for this question, then it's not hard. Otherwise, for some of the students, if you miss 1 or 2 pieces of the critical knowledge points, then you may not get it. Yeah. So the answer 3 multiplications. Yeah. So let me explain why. First, when you look at this special polynomial, can you see it corresponds to 1 row in the Pascal's triangle? Okay, so 1 row in the Pascal's triangle. Okay, yeah. So you look at the structure of the Pascal's triangle. That means this polynomial can be written as x plus 1 to the 6th. Binomial formula. Yeah, because Pascal's triangle corresponds to the binomial formula. Okay? Yeah. How to calculate? We only need to calculate number of multiplications. Yeah. We do not need to calculate number of additions, right? Yeah, number of multiplication. So you calculate the first multiplication, x plus 1 times x plus 1. So you get x plus 1 squared, the first multiplication. Then, after that, you have square times itself, square times another copy of the square, you get to the 6. So 2 more, okay? Multiplication 1, 2, 3. So total 3. Total 3, okay? Yeah. Yeah. So to get this 3, so you need to, to be familiar with, 2 key pieces. The first one, Pascal's triangle. Second, repeated squaring technique. Yeah. These 2 pieces. Yeah. All right. Number 7. Element uniqueness problem. Better than algorithm, better than with growth function n squared, yes. Remember, we did 2 methods. Method 1, that's n squared. Method 2, n log n. And we know this n log n, we did a limit, right? Better than the n squared version. We calculate the limit. Yeah. And that limit tells us this growth function belongs to little o of n squared. That means better than n squared algorithm. Yeah. Number 8. We have an array with more than 2 elements. If it is not sorted, then there must be at least 2 elements that are not in place. True. Yeah. So more than 2. So n greater than 2. All right? Yeah. So the question is, if it's not sorted, that means the number of elements not in place, that number must be greater than 0, right? Yeah. The number of elements not in place must be greater than 0. Otherwise, if it equals 0, that means all elements are in place, right? All elements are in place, that means it's sorted. Okay? Yeah. So that's not true. Based on assumption, it's not sorted. So the number of elements not in place must be strictly greater than 0. Yeah. Then, if it's greater than 0, can that number be 1? Only one element in place, all the other elements not in place? No. Yeah. No, it cannot be 1. Okay? Because if only one element not in place, n minus 1 elements in place, then if n minus 1 element in place, it would force the last element in place, right? Yeah. Because n minus 1 elements all in their right position, the last position left for the last element, that one must be in place. Yeah. So that means it's impossible that number equals 1. Yeah. So then the only thing you can try is 2 elements not in place. Is that possible? Yes. You just swap 2 elements. Okay? So you get an ordered array. That's all in place, right? Then you swap 2 of the elements in an ordered array. So you get it. So, yeah. So yes. Yeah. Swap 2 elements in an ordered array, you get 2 elements not in place. Okay? Yeah. That's simple. Yeah. Yeah. So this question. So you need to know several things. Yeah. Although not very hard. Yeah. Yeah. But you need to do some analysis, simple analysis here. Yeah. Try to understand this question well. Yeah. Because I will give you a similar question in the midterm, yeah, based on this one. Yeah. The number of elements not in place. Okay? So some question related to this one. Yeah. I modified this question slightly. Yeah. So you need to familiar with, all the concepts we used in this question. Yeah. All right. Number 9. If an array does not have any inversion, okay, yeah, which of the following statements is correct? Yeah. Array is in descending order, ascending order, not ordered. Yeah. It's ordered, but in ascending order. Yeah. Then no inversion. Yeah. Zero inversion. Yeah. That's simple. Yeah. The last question. What is the growth function of the running time efficiency function for the bubble sort? That's easy. dn squared. Yeah. Bubble sort, although I didn't write that formula explicitly, yeah, but I said it's the same as the selection sort. Okay? Yeah. So the number of comparisons you need for the bubble sort is this. The same as the selection sort. Yeah. And the growth function here, that's n squared. Growth function. Yeah. Yeah. It's a simple question. Yeah. All right, so let me see how much time I left. Oh, still 10 something minutes. Yeah. Yeah, so we can continue, a small topic about the insertion sort. Yeah. All right, so if you have any question, just let me know. Yeah. So here I didn't see any question from your chat area. So I just keep going. Yeah. But I need to jump to, I need to get out. Oh, yeah. It's quite annoying. Yeah. Get out of the, yeah. So how do I quit? How do I quit? Yeah. Let me see. Yep. End the show. Yeah. Because I need to go back to the discussion here. Okay? All right. Continue the insertion sort. All right. Yeah. Conclusion. Yeah. So after we learned insertion sort, remember? So here, let me refresh your memory a little bit. Yeah. So to make the conclusion, I want to point out one special property for the insertion sort. Yeah. Yeah. So here, I want to use this property. Insertion sort has this property. The worst case efficiency, big theta of n squared. The best case efficiency, big theta of n. Yeah, remember? Yeah. So that's what we did in the first half discussion. What does it tell us? So here, we know the difference is big. The difference, big difference. The difference is big. Okay? Yeah. So what does this property tell us? For the worst case, this n squared performance is very slow. We know it's very slow. But for the best case, this n performance is very fast. Very fast. Yeah. Yeah. So the insertion sort has this property. Its best case efficiency is very fast. This property is useful sometimes in our real world situation. So here I want to emphasize this property. Yeah. So I want to talk about some special application of this property in our real world applications. Yeah. So let me explain this property using a diagram. If the given array is almost sorted, Look at this condition. Almost sorted. So it's not sorted. Okay? First, it's not completely sorted. Yeah. But it's almost sorted. Yeah. Only you can find a few small locations where the elements are not in order. Other than those bad part, small bad part, the remaining elements are in order. Yeah, that property. Okay? Yeah. If your data has that property, then the insertion sort is a good choice to get the whole array sorted. Okay? If your data has that special property, then the insertion sort is the best sorting algorithm to recover the whole array as an ordered array. That property. Okay? Yeah. So if your data has that property. Yeah. All right. So here I use the diagram, I use this line segment to represent our data in an array. Yeah. And for this data, there are a few scattered places, locations. A few scattered locations where the elements are not in order. Other than these, red circle area, the remaining elements all in order. If your data has this property, then the best algorithm to get the whole array sorted, it's the insertion sort. All right? Yeah. That property. Okay? Yeah. So one example, yeah, because sometimes, some people use a situation like in a library, the cards, all the way, how to find books in a library. Okay, so the older way, so when people do not use the computer system, people use library cards, right? Yeah. So library cards, sometimes people change the order a little bit. So yeah, but a few scattered place, it's not ordered. Yeah, the most part ordered. Yeah, so that's the one special situation you may have in the real world. Yeah. But if you happen to get a special situation with this property, then insertion sort is the fastest, because you only need to do big theta of n to get the whole array sorted. Other sorting algorithm, if you use any other sorting algorithm to fix it, the best you can do is big theta of n log n. Okay? Yeah. The best you can do for non-insertion sort. Only insertion sort can give you big theta of n in that situation. Yeah. Almost sorted, that situation, you can get big theta of n. Other, quick sort, any other, even quick sort, you get this efficiency, big theta of n log n, much slower than in the insertion sort. Okay? Yeah. Yeah. So that's the, one important point I want to talk about. Yeah. All right. The next one, I want to show you two examples. Sort 4-element array and sort 5-element array. Yeah. Here, let me just do sort 4-element array today. Yeah. 5-element, so I leave next time. Yeah. After I finish review, I talk about 5-element array problem. 4-element array, sorting 4-element array, because it's very simple. It is related to the insertion sort. Yeah. And very simple, so I can finish it today in a few minutes. Yeah. All right. So let's assume we have 4-element array. Here I use x1, x2, x3, x4. Okay? We want to sort these 4-element array the best we can. We want to use the minimum number of comparisons to sort it for the worst case. Yeah. So that's the whole question. Minimum number of comparisons to sort it for the worst case. So let's do it. Okay? All right. Let's do it by the insertion steps. How about that? Yeah. So we follow the insertion pattern to sort it. Yeah. The first element, x1, it's already sorted, right? The second time we do one comparison, x1, x2, to get it sorted. So let's assume x1 less than x2. Okay? All right. So this is the first comparison. All right. After that, the next time we consider insertion x3, 2 more comparisons to get it 2 more comparison, right? To get it sorted. Let's just write, okay? Let's just get it sorted. Yeah. So the step 2, step 1, one comparison, step 1. Step 2, 2 more, so 1 plus 2, 3, right? Yeah. Step 3. Yeah. Step 3, you already have x1 less than x2 less than x3. Now you have x4, you want to insert it at the right place. Yeah. So the first comparison, you do not compare with x3, you compare it with x2 first. Yeah. Using the binary search way. Here we use the binary search way comparison. Okay? We compare the element in the middle. That's first comparison. Okay? Then there are 2 possibilities. You just need one more comparison. Compare with either x1 or x3. So that means you need 2 more comparisons to get it in place. Right? Yeah. So step 3, you need 2 more. So the total number of comparisons, 1 plus 2 plus 2 equals 5. So you need 5 comparisons to sort 4-element array. That's the solution. Okay. And then later I will show you this 5 comparison solution is optimal. Later I will convince you, I will show you. Okay? So this solution is optimal. Okay? It's optimal. Yeah. Yeah. So here today I give you this solution first. Next time I will give you the sorting 5-element array. That solution. Okay? Yeah. All right, so that's it. So we finish it this class today. Yeah.